Lesson 18, Standard Deviation. The standard deviation is a measure of dispersion or variation of the data. In this instance, the term standard refers to the norm or typical amount, that is, on the average. The term deviation refers to how much a data value differs from a fixed point of reference. The point of reference for the standard deviation is the mean. Putting these two ideas together, we have the standard deviation. The standard deviation measures dispersion by determining how much, on average, the data values vary or deviate about the mean. To illustrate this idea, we can look at some data values on a number line. The point of reference from which the deviations are measured in the standard deviation is the mean. The mean is that center of gravity or balancing point of the data. So, each data value deviates or differs from this mean by a particular distance. Some data values are close to the mean, some data values are moderately away from the mean, and some data values are quite a distance away from the mean. So all the different data values have a different distance or deviation from the mean. What the standard deviation does is calculates a single number that tries to represent the typical or average amount of deviation for all the data values from this mean. So this would be a standard deviation. That value is not as big as the bigger deviations, and it's not as small as the smaller deviations. But the standard deviation is this typical or average amount that the data values differ from this mean. So to deviate from the mean, a standard deviation, you can go both above and below the mean. So here, if we deviate one standard deviation above the mean, notice a standard deviation is that typical average amount. It's not as far as the farthest one, but not as close as the closest one. It's somewhere in the middle. So a standard deviation gives you that middle or average spread of the data. Same is true if you go one deviation below the mean. So here is the same one standard deviation below the mean. It's not as far as the farthest data value from the mean. It's not as near as the closer data values to the mean on the below average side. The population standard deviation is given by the formula sigma sum x, and it is calculated by taking the square root of the sum of the quantity of the population data values minus the population mean quantity squared divided by the population size. The sample standard deviation is given by the formula S sub x, and it is calculated by taking the square root of the quantity, which involves the sum of the sample data values minus the sample means quantity squared divided by the sample size n minus 1. The population standard deviation is denoted by the Greek letter sigma. Subscripts provide clarification. Here, sigma sub capital X is just referring to the population standard deviation for all of the population data values. If the data collected was grade point averages, then we could refer to this as a sigma sub GPA. Since the population standard deviation is calculated based off of a census, that is, all of the data values in the entire population, the population standard deviation is a parameter. The sample standard deviation is denoted by a lowercase s. And again here, subscripts provide clarification. Since the sample standard deviation is calculated based on just part of the population, that is the sample standard deviation is a statistic. Now, in the calculation of the population and sample standard deviations, we have this use of summation notation, where these notations refer to the sum of the data values minus the means. In the population version, it's the capital X, population data values, minus mu sub x, the population means. The capital X minus mu is the actual deviation that that particular data value is from the mean. In the sample version, we have the lowercase x representing the sample data values minus x bar, the sample means. Again here, the x minus x bar is the actual distance or deviation the data value is from that mean. These deviations are then squared in the population and sample standard deviations. The reason for this we saw earlier. Because the mean is the center or balancing point of the data, it basically centers or balances out all the deviations that the data values are from the mean. So when data values fall below the mean, the x minus the mean results in a negative deviation, whereas when data values fall above the mean, their data value x minus the mean produces a positive deviation. And then if we were to just try to average these deviations by summing and dividing by how many deviations we have, the sum of the negative deviations and the positive deviations would always equal 0 because they center or cancel out. So the squaring allows us to make all these deviation values positive. So the negative deviation value squared become positive, the positive deviation value squared become positive. So now when we take a summation, there's no negative to cancel out the positives. Then, to find the overall average amount of these squared deviations, this sum of the squared deviations is divided by capital N in the population case to calculate the population mean squared deviations. In the sample version, this sum of the squared deviations from the sample mean is divided by n minus 1, the sample size minus 1, to calculate what we call an adjusted sample mean squared deviation. These means of the squared deviations is in statistics referred to as the variance. And it turns out that the sample version of the variance, if you do not divide by the n minus 1, actually produces a biased estimate of what the actual population standard deviation is. So in the sample standard deviation, it was determined that the factor to correct for this bias in the estimation of the standard deviation is to divide by the n minus 1 instead of the n. The square root is taken at the very end to counteract the squaring. Because we first initially squared everything, so all the units now are squared. To counteract all the squaring, we then do the inverse of squaring, which is square rooting. And so the ultimate result after doing the square rooting is we get these standard deviations. So now that we've calculated the standard deviation for this student's Unit 1 exam scores, we then need to interpret the result. Now, a description of the result is just reporting the results that we received in the data. In this case, the standard deviation of exam scores for this student's Unit 1 examination is 1.6. Interpretations go beyond just the description. That is, they give meaning or an explanation of what the result is. Now, since a standard deviation is the standard, the average or typical amount of deviations, how far the data value is from the mean, we can interpret this result of 1.6 this way. Thus, on average, this student's Unit 1 examination scores deviated from the mean by about 1.6. To illustrate this idea, we can take this student's Unit 1 examination scores and look at them on a number line. Now, the point of reference used by the standard deviation is the mean. So in the previous problem, we've already determined that the mean for this student's Unit 1 exam scores was 3. What the standard deviation does is calculates how far each data value deviates from this mean of 3, and then tries to find the overall typical amount or average amount of deviation. So the score of 0 deviated 3 points below the mean of 3. A score of 2 on the test deviated 1 point below the mean of 3. The score of 3 deviates 0 points from the mean because it's equal to the mean. The scores of 4 each deviate 1 point above the mean of 3, and a score of 5 deviates 2 points above the mean of 3. So here are all the overall deviations that the data values are from the mean. Notice some data values are close to the mean and some data values are far from the mean. The standard deviation of 1.6 tells us roughly on average how far the data values deviate from the mean. So above the mean, 1.6 is roughly in the middle of the above average group. It's not as far as the +2, but but it's not as near as the +1. Same thing works for below the mean. If you go 1.6 below, 1 standard deviation below, it's roughly between the below average data values. It's not as close to the mean as the -1 deviation, but it's not as far as the -3. Another way of looking at this is you could look at it in scale of the actual data values. If we were to take the mean of 3 and add 1 standard deviation, we'd be going 1 standard deviation above the mean. So 3 plus 1.6 is 4.6. And when you look at the actual scale of the data, a score of a 4.6 on the test value here is somewhere between those 4s and 5s that were the above average test scores. Because a standard deviation gives you this average or middle amount, 1 standard deviation typically puts you in the middle of the above average group. A second standard deviation would put you all the way to the end. So if we go 2 standard deviations above the mean, so that's 3 plus 1.6 once plus 1.6 twice, that's 2 standard deviations above the mean, we get a value of 6.2. And a score of 6.2 on the test goes beyond the biggest value, which is a score of 5. The same thing works for below the mean values. If we were to go 1 standard deviation below the mean, that would be the mean of 3 minus 1.6. 1 standard deviation below gives us a score of 1.4. And a score of 1.4 puts us roughly in the middle of the below average scores, which is between 0 and 2. And since the standard deviation gives you sort of this average or middle deviation from the mean, 1 standard deviation roughly puts you in the middle, in this case, of the below average group. A second standard deviation kind of puts you towards the end. So if you do 2 standard deviations below the mean, that would be 3 minus 1.6 once, minus 1.6 twice, you get a minus 0.2 score, and the minus 0.2 score goes beyond the 0, which was the minimum score. Whenever there is variation in the data, the results are not constant. Some data values will be closer to the mean, and some data values will be farther from the mean. The purpose of the standard deviation is to describe the typical amount of variation that the data values are from the mean. When the data values are clustered near the mean, the standard deviation is small. So to illustrate this, if we have data values very close to the mean, we have a very small deviation. Hence, when we calculate the standard deviation, we'll get a relatively small result. When the data values are scattered far from the mean, the standard deviation is large. So when the data values are far from the mean, the result is a large deviation. Hence, when the standard deviation is calculated, we get a large result. Regardless of the overall amount of dispersion in the data, the standard deviation always indicates that typical deviation from the mean. So a standard deviation is not as far as the largest deviation, but not as small as the smallest deviation. The standard deviation gives you that average, overall, typical deviation the data values are from the mean. Hence, in general, the overall range of the data values is usually encompassed by 2 standard deviations below and 2 standard deviations above the mean. So if you go from the mean 1 standard deviation below, you get to the middle of the below average. When you do a second standard deviation below the mean, you get towards the end of the below average data values. The same is true on the above mean side. If you go 1 standard deviation above the mean, you get to the middle of the above mean values, and a second standard deviation above the mean gets you to the end of the above average data values. Basically, 1 standard deviation from the mean in either direction reaches the middle, and a second standard deviation extends all the way to the end of the data. Since the standard deviation uses the mean as the point of reference to determine the deviations, like the mean, the standard deviation is affected by extreme data values. Thus, the standard deviation could produce distorted results whenever the data values include outliers. So, as long as outliers are not present in the data, The standard deviation is the preferred method for measuring dispersion.